And below the sense amplifiers, you have what is called as a page register, which is a memory, which again includes ECC. It's a memory with ECC. And this ensures quick or decoupling of the speed of the flash from the speed of the processor or the processing system altogether. Because the burst mode and everything can actually be implemented in this page register itself.
Sir, is this composed of SRAM cells?
Sorry?
Stage register is composed of SRAM cells.
It can be SRAM cells, it can be flops. Ideally, because this is a large number of registers, this is a large number of storage elements, you would use an SRAM. An SRAM would be denser. But SRAM would mean a little bit extra complexity also. If you do not want to go into that complexity, you can just make a register bank. Anyway, this cube is very dense.
Okay.
Okay, na? Now, this is the logical view of this. What we are saying is, there is a cell, there is this concept of word, then there is a page. Page is all the bit lines, all the cells sharing the same word line. That is a page. And a block is a group of multiple pages where the bit lines are there are multiple bit lines and both multiple word lines in there. Okay. As I said, entire page is programmed at once and entire block is erased at once. Okay. If you increase the page size, let us say, so यहाँ पे इधर देखते हैं, we increase the memory size 8 MB, say we went to 16 megabit. I maintained same page size and block size. What happens? Read per page remains same because the size of the page had remained same. The program per page remained same, and erase per block, the duration remained same. Now, if I go to a larger memory with, let us say, larger page size now, larger block size now, then you will notice that this timing, program per page timing, can start to reduce a bit. Why would that be the case? Hello?
So because more number of cells have been programmed at once.
Because your page size has increased. So if you wanted to update a particular file, you now need lesser program operations. If you change the block size, then what happens? Then you notice the erase time over here has reduced. Because you erase the entire block in one go. Now that size has increased, so the erase time has reduced. Over here, we saw a significant reduction in, how do we put it? Program time. We also saw a reduction in page time, in the erase time, but that was the major chunk over here, and that has reduced. Okay. So if you're talking about, I'm sorry, I'll just take another 1 minute, because I want you to be prepared for Kalyan's lecture. That's it, just 2 more slides. We're talking about 125 millimeter square, 1 gigabit NAND flash. Then these are the numbers that you could look at. Just keep these numbers in mind and then compare with the numbers that Kalyan may share tomorrow, on day after tomorrow. Okay. And you can actually find out read speeds, the same kind of formula that we used when we were working on DRAM, when finding the peak bandwidth over there. Exactly the same way, you just need to understand how the page is organized, what kind of time it takes for data transfer, what kind of time it takes for command transfer, number of cycles for command transfer, and so on. And you can arrive at read speed, write speed, and erase speed. And you see, erase speed is much, much faster. Why?
Complete block is erased.
The complete block gets erased in one go. So the total amount of time you need is lesser. However, realize that you need 2 milliseconds to erase. You need 2 milliseconds to erase. But because now the number of times this erase has to happen is lesser, overall erase speed is much higher. Okay. Now a quick comparison between NAND and NOR. NOR is very high speed random access and byte programming. Over here, high speed programming, high speed erasing, small block size, but it has very slow random access. Additionally, byte programming cannot be done. For the NOR, the programming and erase are also slow. And NOR flash could be suitable for replacement of EPROMs, and because these are usually smaller in size, whereas NAND flash can actually be used as a data memory. All the SD cards that we use, they're all NAND flash because it's dense, therefore cheaper. Okay, any questions?
Sir, in page register, what will be the mechanism of burst access there? In DRAM, we saw that first we give the row, we do row decoding, and then we give columns address, and we taking the burst. But here, what we will do? How we will do?
So all those schemes that we looked at in DRAM can also be explored to be used here, because they're not linked to data to the DRAM per se, are they? No, they are all about inter-chip data transfer. So all those schemes you can put over here also in control by controlling it.
Okay, sir. One more confusion then, sir. We initially saw when we see the timing diagram, we were initially sending the column address, and then we are sending the row address. So would it create any rates condition during the burst mode access?
So again, you would want to do it according to what is the requirement there. Okay. So यहाँ पे when you select one particular row, you are actually selecting the entire page, reading the entire page anyways. So you may not need any further thing for burst mode access, something like inside the memory. आप उसको जब अपने नीचे के SRAM के plane पे ले आए, when you brought it to the plane of your SRAM, then you can decide whether to how fast or how slow to read there.
ओके मतलब पहले SRAM के प्लेन पे ला देंगे, फिर उसके बाद बर्स्ट मोड
Okay.